I welcome to all. Myself is Ms.S.Subbulakshmi, Assistant Professor of Youth Department, Bharat Institute of Science and Technology, BIHER. Going to give a lecture on network theory, which will guide us in power management, understanding signal and system, data type of digital or analog, understanding associated technology. Content of my lecture as follows. Law, Kirchhoff's laws, voltage and current division rules, mesh analysis, nodal analysis, superposition theorem, Thevenin theorem, Norton theorem, maximum power transfer theorem, and the Telegram theorem. Hope some of the laws are familiar at school level. So today classes I am going to discuss about laws. Ohm's laws is to define the relation between voltage, current, and resistance in the electric circuits. So, Ohm's laws is current in the resistor, variation in direct proportional to the voltage applied to it and is inversely proportional to the resistor value. So stated mathematically I equal to V by R, where I is the current, V is the potential difference of volt, R is the resistance in ohm. So Kirchhoff's laws, Kirchhoff's circuits law are two equality that deal with the conservation of charge and energy in electrical circuit. There are basically two Kirchhoff's laws. First one is Kirchhoff's current law is based on the principle of conservation of electric charge. Kirchhoff's voltage law is based on principle of conservation of energy. So Kirchhoff's current law, this law is also called Kirchhoff's first law, Kirchhoff's point rules, Kirchhoff's junction rule, and the Kirchhoff's first rules. The principle of conservation of electric charge implies that at any node in the electrical circuit, the sum of current flowing into the node is equal to the sum of current flowing out of the node, or the algebraic sum of current in the network of conductor meeting at a point is zero. So, shown in the diagram, the current I1 is the leading current, I2 is entering current, I3 also entering current, I4 is leading current. So we can written as according to the KCL, I4 plus I1 plus I4 equal to I2 plus I3. So recalling that current is a sign positive or negative quantity reflecting direction towards or away from the node. This principle can be stated as summation of I equal to 0. So Kirchhoff's voltage law, this law also called Kirchhoff's second law, Kirchhoff's loop current loop rule, and Kirchhoff's second rule. The principle of conservation of energy implies that the directed sum of the electrical potential difference around the closed circuit is 0, or more simply the sum of the EMF in any closed loop is equivalent to the sum of the potential drop in that loop. So algebraic sum of product of the resistance of the conductor and the current in the closed loop is equal to the total EMF available in that loop. So summation of voltage EMF equal to I into summation of resistance value. So the sum of all the voltage around the loop is equal to be 0. So V1 plus V2 plus V3 minus of V4 equal to 0.
Rules. So introduction of voltage and current division rules. So Kirchhoff voltage law state that the algebraic sum of the voltage in the loop must equal to be 0. So practically application of this law is the voltage division rule. The Kirchhoff current law is state that the algebraic sum of all current entering and the existing node must equal to be 0. So practical of application of this law is also called current divider rule. So a parallel circuit acts as the current divider as the current divides in all branches in a parallel circuit. So a series circuit acts as a voltage divider as a voltage divides in all branches in the series circuit. So voltage division rules calculate equivalent resistance in series. So R equivalent equal to R1 plus R2 plus R3 the number of current. So calculate the current by applying Ohm's law I equal to V by R equivalent. So current remain same in the series. So I equal to I1 equal to I2 equal to I3. So as current divider in series, so voltage divider rule state that Vx equal to V into Rx by Rx divided by Rx plus Ry plus Rx. So example of voltage divider rules. So V1 equal to R1 divided by V1 plus R2 R3 into total voltage. So V1 equal to 5 divided by 5 plus 10 plus 7.5 into 45 volt. So which is equal to V1 value is 10 volt. So V2 what? Already you find out V1 value. So V1 divided by R1 plus R2 plus R3 into V2 total voltage. So 10 divided by 2.25 5 into 45. So V2 which is equal to 20 volt. So application of voltage divisions divider rule. The voltage divider is usually only there where the voltage is regulated by dropping a particular voltage in the circuit. It's mainly used in some system where the energy efficiency does not necessary to be considered seriously. In our daily life is mostly commonly the voltage divider used in the potentiometer. The best example of the potentiometer are a volume turning knob attached to our music system and radio transistor. Next one. So current division rules. So current division rules is calculate the equivalent resistance in parallel circuits. So R equivalent which is equal to R1 into R2 into R3 divided by R2 into R3 plus R1 into R3 plus R2 into R1. So calculate the current by applying Ohm's law. I equal to V by R equivalent. So as voltage remaining same in parallel circuit. So V1 equal to V2 equal to V3 equal to V, which is equal to B as current divider in parallel circuit. So according to the current divider rules, I into equal to RT divided by Rx into I. So example of current division rules, I1 divided by R equivalent, which is equal to 1 divided by R1. So R1 value is can be written as R1 by R1 plus 3 by R2 plus 2 by R3. So R equivalent circuit which is equal to 0.54 ohms. So total current equal to V by R equal or R equivalent. So IT equal to 11.11 amperes. So I1 equal to RT divided by R1 into IT. So you apply the value of RT I1. So we can written as I1 equal to 6 amps. So I2 equal to RT divided by R2 into IT. So I2 value is what? 2 amperes. So I3 equal to 2.97 ampere. So application of current division rules. So current divider circuit also find the application of electric meter circuit where a fraction of measured current is decided to be routed through a sensitive direction device. So using the current divider formula, the proper shunt resistor can be sized to propagation just the right amount of current for the device in any given instance. So mesh analysis is a method that is used to solve planar circuit for the current at any place in the circuit. Planar circuit or circuit that can be drawn in a plane surface with no wire crossing each other. Mesh analysis work by randomly assigning mesh current in the essential meshes. And essential meshes is a loop in the circuit that does not contain any other loop. So step 2 determine the mesh current. Assign a mesh current I1, I2, I2 meshes. So current direction need to be same in all meshes, either clockwise direction or anti-clockwise directions. So apply KVL to each of the meshes. Use Ohm's law to express the voltage in terms of mesh current. Solve the resulting n simultaneous equation to get the mesh current. So, the example of meshes. a circuit with two meshes, so showing diagram. It has two voltages V1, V2, and the resistor of R1, R2, R3, and the current I1, I2, I3 is flow through. So apply KVL to each meshes for mesh 1 minus V1 plus R1 I1 plus R3 into I1 minus I2 to 0. So R1 common term of I1 into common term in I1 is R1 plus R3 here. So common term of R1 and R3. So I1 equal to minus R3, I2 equal to V1 for mesh 2. So R2 I2 plus V2 plus R3 I2 minus I1 equal to 0. So minus of R3 I1 plus R2 plus R3 into I2 equal to, which is equal to minus V2. So solve the mesh current. So R1 plus R3 minus R3 minus R3 R2 plus R3 into I1 I2 equal to V1 minus of V2. Solving this matrix method to find the mesh current by substituting V1 and V2 values. So I1, I3 also already know that I1 minus I2. So nodal analysis, electric circuit analysis, nodal analysis, voltage analysis, or branch current method is a method of determining the voltage between nodes in the electrical circuit in term of branch current. So nodal analysis is possible when all the circuit element branch equivalent relation have an admittance reference predictions. Step for nodal analysis. Note all connected wire segment in the circuit with node of the nodal analysis. So select one node as a ground reference. The choice does not affect the result and it's just a matter of conversions. So choosing the node with the most connection can simplify the analysis. So assign a variable for each node whose voltage is unknown. If the voltage is already known, it's not necessary to assign the variable. So if there are voltage source between two unknown voltage join the two nodes as a supernode, the current of the two nodes are combined in a single equation and a new equation for the voltage is formed. So solve the system of simultaneous equation for each unknown voltage. So this is the example of nodal analysis. So first one, reference node. First you can take reference node. The reference node is also called the ground node. So ground node. So where V equal to 0. So V1 here is V1, V2, V3 or unknown. So which we solve using KCL. So step for nodal analysis, choose a reference node, assign node voltage to the other node, apply the KCL to each node other than the reference node. So express the current in terms of the node voltages. Solve the resulting system of linear equation for the node voltages. So current and node voltage V1 minus V2 equal to 0. So we can written as V1 divided by 500 ohms. Here is V1 minus of V2 divided by 500 ohms. So KCL at node 1, here is I1 equal to V1 minus V2 divided by 500 plus V1 divided by 500 ohms. So KCL at node 2, here is V1 minus V2 divided by 500 plus V2 divided by 1 kilo ohms plus V2 minus V3 divided by 500 ohms, which is equal to 0. So KCL at node 3, here is V3 minus V2 divided by 500 ohms plus V3 divided by 500 ohms, which is equal to I2. So superposition theorem is used to find the solution to networks with two or more sources that are not in series or parallel. The current through the or voltage across an element in the line bilateral network is equal to the algebraic sum of current or voltage produced independently by the source. So for the two source network, if the current produced by one source in one direction, while that produced by other in the opposite direction, that the same resistor, the resulting current is the difference of the two and as the direction of the wall. So to solve the circuit using superposition theorem, first one is to suppress the voltage source, replace with a short circuit. Second one is to suppress a current source, replace with a open circuit. So example of determine the branches of current using superposition theorems. So solution, the application of superposition theorem is shown in figure 1. So where it is used to the calculate the branch current. To calculate the branch current, the node voltage across to the 3 kilo ohms must be known. Therefore, V1 minus 120 divided by 6 plus V1 divided by 3 ohms plus V1 divided by 2 plus 4 ohms, which is equal to 0, where V1 equal to 30 volt. The equation for the current in each branch, so I1 dash equal to 120 minus 30 divided by 6, which is equal to 15 amps. So I1 double I2 double I2 dash equal to 30 divided by 3, which is equal to 10 amps. So I3 equal to I4 dash, which is equal to 30 by 6. So answer of which is equal to 5 amps. So in order to calculate the current by the current source, we deactivate the voltage source, which is the short circuit as shown. So determine the branch current, solve the node voltage across the V3 ohms and 4 ohms resistor is shown in figure. So V3 divided by 3 plus V3 divided by 6 plus V3 minus V4 divided by 2, which is equal to 0. So V4 minus 3 divided by 2 plus V4 divided by 4 plus 12, which is equal to 0. The two node voltage are, by solving this equation, we obtain V3 equal to minus 12 volt, V4 equal to minus 24 volt. So now we can find the branch current. I1 double dash equal to minus V3 by 6 equal to 12 by 6, which is equal to 2 amps. So I2 double dash equal to V3 divided by 3 equal to minus 12 by 3, which is equal to minus 4 amps. So I3 double dash equal to V3 minus V4 divided by 2 equal to minus 1 plus 24 divided by 2, which is equal to 6 amps. So I4 double dash equal to V4 divided by 4 minus 24 divided by 4 minus, which is equal to minus 6 amps. To find the actual current of the circuit or the current due to both the current and voltage source. So I1 equal to I1 dash plus I1 double dash, which is equal to 15 plus 2, which is equal to 17 amps. So I2 equal to I2 dash plus I2 double dash equal to 10 minus of 4, which is equal to 6 amps. So I3 equal to I3 dash plus I3 double dash, which is equal to 5 plus 6 equal to 11 amps. So I4 equal to I4 dash plus I4 double dash equal to 5 minus 3, which is equal to minus 1 amps. So Thevenin theorem or linear electrical networks state that and combination of voltage source, current sources, and resistor with two terminals is electrically equivalent to the single voltage source V and a single resistor, series resistor or. So any two-terminal linear bilateral DC network can be replaced by the equivalent circuits consisting of voltage source and a series resistor. So this is the equivalent circuit of Thevenin theorems. So calculating the Thevenin equivalent sequence to proper value of RTH and VTH. To first remove the portion of the network across which the Thevenin equation circuit to be found. In the figure below, this requires that the load resistance model to be temporarily removed from the network. So second is mark the terminal of the remaining two terminal networks. So RTH, calculate for RTH by first setting all sources to be 0 and then finding the resultant resistance between the two marked terminal. So ETH, calculate the ETH by first returning all sources to be portion and finding the open circuit voltage between the marked terminal. So conclusion, draw the Thevenin equivalent circuits with the portion of the circuit previously removed, replaced between the terminal of equivalent circuit. This step is indicated by the placement of resistor RL between the terminal of Thevenin equivalent circuit. So another way of calculating the Thevenin equivalent, measuring the VOC and ISC. The Thevenin voltage is again determining measuring the open circuit voltage across the terminal of interest, that is ETH equal to VOC. To determine the RTH, a short circuit condition is established across the terminal of the interest and the current through the short circuit ISC is measured with the ammeter. So using Ohm's law, RTH equal to VOC divided by ISC. So find the Thevenin equivalent circuit is a solution in order to find Thevenin equivalent circuit for the circuit shown in figure 1. So calculate the open circuit voltage VAB at when the AB terminal are open. There is no current flow in the flow to 4 kiloohms, 4 ohms resistor. Therefore, the voltage VAB is the same as the voltage across the 3 amps current source labeled V1. So to find the voltage V1, solve the equation for the single node voltage. So by choosing the bottom right node as the reference node, so V1 minus 25 divided by 5 plus V1 divided by 20 minus 3, which is equal to 0. By solving the equation V1 equal to 32 volt, therefore the Thevenin voltage VTH for the circuit is 32 volt. The next step is to be short circuit the terminal and find the short circuit current for the circuit shown in diagram 2, figure 2. So note the current is the same direction as falling voltage at the terminal. So current ISC can be found if V2 is known. So by using the bottom right the reference node, the equation for V2 became the solving above equation V2 equal to 16 volt. Therefore, the short circuit, the current ISC is V2 minus 25 divided by 5 plus V2 divided by 20 minus 3 plus V2 divided by 4, which is equal to 0. Therefore, ISC equal to 16 divided by 4, which is equal to 4 amps. So, Thevenin resistance RTH is RTH equal to VTH divided by ISC equal to 32 divided by 4 amps, which is equal to 8 ohms. The figure 3 show that equivalent Thevenin equivalent circuit for the figure 1.
Norton theorem, IN is calculated IN by the first returning all sources to the original portion and then finding the short circuit current between the marked terminal. So it is the same current that would be measured by an ammeter placed between the marked terminals. So conclusion, draw the Norton equivalent circuit with the portion of the circuit previously replaced between the terminal of equivalent circuit. So derive the Norton equivalent circuit. Solution step 1. The source transformation. The 25 volt voltage source is converted to the 5 amps current source. Shown diagram. So combination of parallel source and parallel resistance. Step 3. The source transformation combined series resistance to produce the Thevenin equivalent circuit. So source transformation to produce the Norton equivalent circuit, the current source is 4 amps. Maximum power transfer theorem. The maximum power transfer theorem states that to obtain maximum external power from a source with a finite internal resistance, the resistance of the load must be equal to the resistance of the source as viewed from the output terminal. So a load will receive maximum power from the linear bilateral DC network when its total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. So RL equal to RTH. So maximum power transfer happens when the load resistance RL is equal to the Thevenin equivalent resistance RTH. To find the maximum power delivered to the RTH equal to RL. So P maximum equal to V square TH divided by 4 RTH, where RL equal to RTH. How to solve the maximum power transfer theorem? Step 1, remove the load resistance of the circuit. Step 2, find the Thevenin resistance of the source network looking through the open circuited load terminals. Step 3, answer the maximum power transfer theorem. RTH is the load resistance of the network. So RL equal to RTH that allowed maximum power transfer. Telegram theorem. So statement of Telegram theorem. This theorem states that any time T, the algebraic sum of instantaneous power in n branches of any network is 0 if KCL and KVL are satisfied, and mathematically summation of n k equal to 1 Vk into Ik equal to 0. So where Vk is the instantaneous voltage drops in the each branch, Ik is the which is equal to instantaneous current in the each branch. So to consider the network shown in figure 1, so where V1 is the 6 volt, V2 4 volt, V3 is assigned to the 3 volt, V4 also 1 volt, and the current is assigned to be I1 equal to 5 amps, I2 2 amps, I3 3 amps, and I4 equal to 3 amps. So step 1, so verification of KCL at node A, I1 which is equal to I2 plus I3. So I1 value is I5 which is equal to 2 plus 3 equal to 5. So at node P, I3 equal to I4. So I3 value is 3 is equal to I4 value of 3. So step 3, verification of KVL in mesh 1. So minus V1 minus V2 plus V0 equal to 0. So V1 value is a minus 6, V2 value also minus 4 plus 10 which is equal to 0. So in mesh 2, V2 minus V3 minus V4 equal to 0. So 4 minus of 3 minus 1 which is equal to 0. Hence KVL and KVL are satisfied. So calculation of power in each branches. So V1 into I1 equal to minus 6 into 5 which is equal to minus 30 watts. So minus V2 into I2 which is equal to minus 4 into 2 which is equal to minus 8 watts. After minus 3 into I3 equal to minus 3 into minus 3 which is equal to minus 9 watts. So V4 into I4 equal to minus 1 into 3 equal to minus 3 watts. So V0 into I1 equal to 10 into 5 which is equal to 500 watts. The Telegram theorem state that summation of n k equal to 1. So Vk Ik is equal to minus 3, minus 8, minus 9, minus 3 plus 50 which is equal to 0. So V1, V2, V3, V4, V0 values applied this equation. So we get the value of power supplied which is equal to 500 watts and the power dissipated equal to minus 50 watts. So application of network theorem. The network theorem are useful in simplifying analyzing of some circuits. But the more useful aspect of network theorem is in the insight which provides into the property and behavior of circuits. Network theorems also help in visualizing the proper response of complex networks. The superposition theorem find use in the study of alternating current and semiconductor circuits where sometimes AC is often with the DC. Thank you.